Hi, my name is Mitchell Lord, and this is my lab report for Lab 4. The purpose of this lab was to analyze the two-dimensional motion of a spring mass system using tracker and to create a computational model of the experiment using the energy principle and Newton's second law. To conduct this experiment, I used tracker to analyze the provided spring video and extract position versus time data. Then I created a computational model using Newton's second law and the energy principle and compared it against the experimental data. Here's a brief preview of my results. The graph on the left represents a change in energy versus time, tracking things such as the change in kinetic energy, gravitational potential energy, and spring energy, and summing it up to make the total energy line, which is this black line in the center, which is constant. These graphs on the right are position versus time, with the top graph being x position and the bottom graph being y position. Here are the physics principles used in this lab. The lab centers around Newton's second law, which states that the acceleration of a system is determined by the force acting on it. It's used to update the system's position and velocity during the loop. The lab also uses the energy principle. We use kinetic and potential energy to calculate the total energy throughout the simulation. By plotting these changes in energy, we can determine whether the total energy of the system remains constant, indicating that the energy principle is satisfied. Here are the equations used: Newton's second law, position and velocity update formula, the energy principle. The formulas for kinetic energy, gravitational potential energy, spring potential energy, the force of gravity, and the spring force. In this experiment, the system consists of the mass attached to the spring itself, and Earth. We assume there are no significant interactions with the surroundings. I calibrated tracker using the distance from the fixed attachment point to the center of the mass, which was given to be 0.7 meters. I then centered the coordinate system at the fixed attachment point with positive y pointing up and positive x pointing right. Here are the initial conditions. The initial position, which I got from tracker, is this. The initial velocity is 0, and the initial time is 0. Here's a video of me analyzing the experiment in tracker. I began by calculating the period of oscillation of the spring using the Y position data from tracker, and I used it to calculate the spring constant K. Then I used the fact that the system is in static equilibrium to calculate the relaxed length L0 of the spring, and then I finally calculated the initial energies of the system using the equations mentioned previously. Here's the math that I used to calculate those things. On the left is the math for the period of oscillation. In the middle is the calculation of the spring constant, and on the right is the calculation of the relaxed length of the spring. For the coding, I began by assigning all the initial values to their appropriate variables, and then at each time step of the main loop, I calculated the net force acting on the system, which consists of the gravity force and the spring force. I used Newton's second law to update position and velocity, and then I used the energy equations to update energies. And then at the end, I compared the model's predictions with the experimental observations. Here are some snippets of my code. On the left, I have the initial setup, the initial mass, position, velocity, etc. And then here on the right is the main loop of the code where I calculate the net force, update positions and velocities, update the length of the spring, and update the energies. Here's a video of the output of my code. The blue ball is the computational model, and the other one is the experimental observations. Here are the results of the experiment. On the left is energy versus time. As you can see, all of the kinetic and potential energies fluctuated throughout the experiment, but the black line in the center represents the total energy of the system, which remained constant throughout the experiment, which is what we would expect from the energy principle. On the right here is position versus time data. The top graph is the x position and the bottom is y. And the blue line is the computational model and the other one is the experimental observations. As you can see, they do follow each other pretty closely, but there's a little bit of error in between the lines. As for the possible sources of error in this experiment, there could have been a tracker area. The track point may not have been placed in exactly the same location on the mass in every frame. There could have been a calibration error. Small errors in setting the calibration stick or coordinate axes affect all the measured positions. And lastly, model assumptions. The computational model neglects effects such as air resistance, spring mass, and internal damping. What does it mean? Is the energy principle satisfied? And yes, the energy principle is satisfied in this experiment because the total energy remains constant throughout the simulation. As the mass moves, kinetic energy, gravitational energy, and spring energy fluctuate. However, the total change in energy remains close to zero, indicating that energy is conserved. The period of oscillation I used in the experiment was based on the Y position data, and its value was 1.519 seconds. I used the same process to calculate the period of oscillation using the X position data instead and got t equals 1.65 seconds. These periods are similar but not identical. This is because the motion is a combination of horizontal swinging and vertical spring oscillations. Small differences are also expected due to experimental uncertainty, tracker measurement error, and simplifying assumptions used in the computational model. Thank you.